Okay, this is the final class of mathematical physics this semester, and we are going to cover the journey of vector calculus, and sometimes it's called calculus about grade, diff, and curl. We have already went through half of the journey. Therefore, I think you are more or less familiar with grade, the gradient, and diff, the divergence. And we'll talk today about the curl, the third ingredients of vectors calculus. Let me put the goal first. The goal of this whole journey is to complete the goal of the journey is to convert the complete Maxwell equation in integral form into a differential formulation. For example, on this transparency, the left-hand side are the Maxwell equation in integral form. Usually, we introduce this kind of form in general physics because it is easier intuitively for beginners. However, as I told you last time, it is very difficult to calculate, to do a theoretical calculation. Therefore, we usually convert these four equations into their differential form on the right-hand side. I would tell you in detail the difference between them. However, they are equivalent to each other, the two forms of Maxwell equation. And it will form the basis of your learning in the sophomore electromagnetism. Usually, the professor will go very quickly through this conversion again in electromagnetism. Okay, and if you are not familiar with these the differential form of Maxwell equation, it will be very difficult for you to follow the rest of the course. Okay, so therefore, this course will provide you with the first beginning of this conversion, and I hope it will help you in your electromagnetic course. And for our purpose, we not only want to convert the Maxwell equation into the differential form, we also have a second goal, which is essential to our class. That is, we want to use this Maxwell equation, again, in differential form to derive the electromagnetic wave equation. You will see that using the differential form, the electromagnetic wave equation could be easy to derive in just one transparency, okay? Even though it's a little bit mathematical and abstract, however, it's very brief and it's very fast. At the bottom of the transparency, you can see that the gradient square, which we will introduce, that's the Laplacian. You can think of it as the second derivative of x equal to mu 0 epsilon 0 e, the time derivative, partial derivative, okay? As you may remember, this is actually very similar to, actually, it is the same wave equation we have derived in the continuum limit of the couple oscillation. Okay, so that's the goal. We will finish today. Last week, we are half through the journey. We started already to tell you about the partial differentiation in space of a scalar function. You can put the electric potential in your mind as an example, but as I have emphasized so many times, this material, the theorem, and the facts we outline in the lecture is not only applied to the electric potential. In fact, any scalar function could be the subject of our theorem. Okay, so it's very important. But however, it is usually easy to start with a concrete example to comprehend the abstract concepts. So that's why we started with the electric potential as our example. Okay, so we introduced the electric potential as the example of scalar function in space, and then we take the three partial differentiation with respect to x, y, and z. It seems these three vectors or these three functions, it looks like they form a vector. They form a vector. And because it depends on the space x and y and z, this should be z, x, y, and z, therefore this is a vector field, because a vector field means it is a function of space, the coordinates, however, the value of the function is a vector. Okay, so we derive that if we assume that the difference of electric potential equals the line integral of electric field, then the electric field is equal to the gradient partial v, partial x, partial v, partial y, partial v, partial z, the vector we form using these three partial differentiation. So these three partial differentiation put together as three components look really like a vector. So therefore we give it a notation which indicates these facts explicitly. So this vector will be called the gradient of phi. And with this reverse triangle, we put a vector, an arrow on the top of it, so that to indicate again, this is actually a vector. So this however, you still need to remember this reverse triangle, so-called grade, is actually an operation instead of a number, or function. So it's an operation, therefore it needs to act on something to produce a concrete result. Okay, so for example, in this case, the grade is acting on phi that produce a vector field. If this V is electric field, then this, if this phi is the electric potential, then the gradient of phi will be equal to the electric field. That's the example we have already talked about in the last lecture. And so this notation is beautiful, okay? Even though it needs to act on something, but taken individually, it just indicate it is a derivative differentiation, or you call partial derivative, and you also indicate the three components from a vector. Whenever it acts on a function, it becomes a vector. We also emphasize that, so a good example is to calculate the electric potential of a fixed charge or point charge. We have already known the electric potential of a point charge equal to this formula. Then you can calculate the electric field, that is the Coulomb electric field, directly from this electric potential by taking a gradient. So E is equal to minus grade V. So it's in our exercise, it's in our homework, the last homework, I think it's homework number 5. This is one of the problems. So the result, of course, will be equal to this, okay? The usual electric field of a point charge we have emphasized so many times in class. And yeah, so try to do this homework. In next lecture, maybe I'll give you some comments about how to do it. But this is a very, very useful and important and interesting exercise you can do at this point. Okay, then with gradient in our hand, when we do gradient, it usually acts on a scalar function. However, it could also act on electric field, as we emphasized last time. For example, this partial differentiation can act on the electric field. For example, you can take the partial derivative of Ex over X, Ex over Y. These are all possible. However, to form something useful, you have to remember the gradient has 3 components, electric field has 3 components. Therefore, the index I mean X, Y, Z, or you prefer to call it 1, 2, 3. It's up to you. Anyway, the space indices has to be arranged in a meaningful way so that the quantity you define is useful. You can define it anyway. However, to be useful, usually the indices has to be defined, has to be arranged in one of the two ways. The first is to put them in like inner products. By inner product, we usually match the indices of the two vectors, x matching x, y matching y, z matching z, and then add them together. That's the usual inner product we do in vector analysis. Therefore, we can do the same. We take the ex and partial x, and the ey, partial y, ez, partial z, and add them together. And because E is behind the gradient, that means it is acted on by this gradient. So the Ex is taken the X partial differentiation, Ey taking the Y partial differentiation, and Ez is taking the Z partial differentiation. And then after this is done, then we add them together, and it comes as a scalar, as we would expect from the inner product. Okay, so this quantity is very useful. We call it the divergence, or diff in short. Okay, and in last week we have already demonstrated in class this divergence is very useful to transform the Gauss law from integration formula to the differential formulation. Okay, so we'll review it again today. Another possibility is to arrange the space indices into a cross products. That is, we match, again, we still use the gradient to act on the E. So you can see the components of the electric field is acted on by the partial differentiation. But we arrange the indices of the two into a form of cross products. For example, the cross product, the X component of X product will be YZ minus ZY. Okay, therefore it would correspond to the Y component of the first vector times the Z component of the second vector minus the Z component of the first vector times the second Y component of the second vector. Okay, so you put everything together, you will define the first component of the cross product of gradient and E as partial EZ, partial Y, minus partial EY, partial Z. Okay, and the rest apply the same procedure applies to the rest of the vector. We can put it this way. Okay, after class I will add a definition of a usual A cross B, the cross product of two vectors, so that you can compare the two together, so that you understand why we will define this thing as the cross product. Remember, if grade and E are vectors, then the cross product between them is a vector. Therefore, you expect this thing we just defined as a vector field, instead of just a scalar field. So that's the difference between the two definitions. So the second definition will give you the curl. In Chinese, it's called 旋度. In English, it's called curl. It's curl. It will indicate. We'll see very soon today. It will calculate the way the degree of field will circulate around an axis. Okay, that's why it is called curl. In Chinese, 它是会算出一个向量场的一个回旋的这个程度啊，所以这个 curl 指的就是像这样子的一个旋度。So somehow it is easier to say in Chinese. Okay, so we define two quantities or two functions or two operations of a vector field by the gradient. Then the point is that these two definitions are useful when we want to connect the integration in space to the differentiation in space. Okay, this connection are usually called integration theorem. It applies to two different kinds of integral in space. One is the surface integral and the other is line integral. We'll start with the first surface integral. The surface integral is about the Gauss's law. Gauss's law is covered extensively in the general physics, but here I will still again lay out some definitions so that you remember, you will memorize some of, you'll recall some of the details of this very, very beautiful theorem so that we can go from integral formulation to the differential formulation. Okay, so the Gauss's law is about a quantity, a physical quantity we call electric flux. In this notation, it is usually written as phi E. It is defined as the inner product of electric field and A vector. A vector is about an area. This area, usually it's easy, we can define for a plane area, 平面，小小的这个平面。And by A vector, I mean the magnitude of this vector, it's an artificial vector because an area is an area. It is hard to say, to choose. It is hard to visualize it as a vector with an arrow. However, for physics and also for mathematics, we find it useful to define a vector for this area with the area 面积 as the magnitude of this vector and the direction we choose the normal direction, the direction normal to the area as the direction for this A vector. Okay, so here is a diagram to show you the direction and magnitude of this A. And if I I take the inner product of electric field and this A vector, we obtain the electric flux. Okay, therefore you can see that this electric flux depends on the angle between A and the electric field. If they are perpendicular to each other, then E dot A, the electric field, is just equal to the product of E times A. However, if there is an angle, then you have to multiply by the cosine theta. Okay, so by this definition, we can easily see that there is a physical meaning of this definition, electric flux. It is equal to the number of it is equal to the number of electric line flowing through this surface. For example, in this little diagram, on this small plane here, the direction, the vector is in this direction. Then if you calculate the flux of this small plane, then it will give you the number of electric field flowing through it, like this. Okay, and however, if the electric field is in the opposite direction, not really opposite, but in the separate direction of dA, like the left-hand side example, then the cosine theta will be larger than 90 degrees. Therefore, E dot dA, the electric flux across this, through this plane, will be negative. That's good because then we can know the direction of the electric line flowing through the surface. If it is negative, if it is positive, so that means the E is in the direction of dA. However, if it is opposite to each other, then the electric flux is negative, then it means the electric field is flowing opposite to the direction of the plane. With this definition, then we can define the electric flux through a closed surface here, as defined here. This is a closed surface, and we can define the direction of the surface to be from inside to the outside, usually called outward or outward perpendicular, because it is perpendicular to the surface. In this way, then the flux we just defined has a very, very simple meaning. Because if the electric line is flowing in the direction of dA, that means it is flowing from inside to the outside. Okay, so the contribution to the electric flux will be positive if electric field line is flowing from inside to outside. I would say it is leaving this closed surface. However, in the second case, when the electric field is flowing opposite to the direction of dA, the contribution will be negative. So that means the electric line is flowing from outside inward into the closed surface, because the dA is pointing from inside to outside. Okay, so if E is in the opposite direction of dA, then E will be flowing from outside to inside. Okay, therefore, if it electric field, so we reverse the logic. If the electric field line is flowing into the surface, closed surface, the contribution to electric flux will be negative. So sum up everything together, when I calculate the total, therefore I can define a total of electric flux through a closed surface. A total flux through a closed surface will be defined as if I divided this closed surface into small pieces, and then calculate the electric flux through every small pieces, and then sum them up, and then take the limit n equal to infinity. Okay, and this definition will be converted into the integral of the surface integral of electric field. Okay, so this is I'm only reviewing the general physics coverage of the Gauss's law. Anyway, so if I define the electric flux in this way, then it has a very, very simple physical meaning. The electric flux, as I have said, if the electric flux is about the number of electric field flowing through the surface. However, if it is leaving the surface from inside out, then its contribution is positive. If it is entering the surface, then the contribution will be negative. So to sum up, the total flux will be the number of electric line leaving the surface minus the number of electric lines entering the surface. So that's why this flux is very useful, because it has a very, very simple physical meaning. Okay, so then with this simple physical meaning in mind, we can derive the Gauss's law very simply from physical intuition. Okay, if there is no charge inside a closed surface, usually we call it Gaussian surface, then if there is no electric charge inside, there is nowhere this electric line will vanish, and there is nowhere the electric field line will be generated. So every electric line entering the closed surface will leave at the end. Therefore, the number of electric line leaving will minus the number of electric line entering must equal to zero. Must be equal to zero. Okay, so we got a very, very simple quantitative formula quantitative law for this quantity, the electric field. Okay, and then if there is a charge, you may ask, if there is a charge inside the Gaussian surface, what will happen? Now, the total flux will not be equal to zero, because the sum of the electric field line will be generated inside the Gaussian surface, and therefore there will be more leaving the surface than entering the surface. However, the point is, whatever the size of the Gaussian surface, as long as the Gaussian surface encircles a charged particle, then the flux will be the same. it is easy to calculate this electric field, electric flux, because once the electric field line is generated by a charge, then it will go through S1 as well as S2 as well as S3. Therefore, I will say the electric flux will be independent of the shape, the position, and the size of the Gaussian surface. Okay, put the logic in reverse, we arrive at the Gaussian law. The Gaussian law in integration formulation. That is, the electric flux defined as the surface integral of electric field on a Gaussian surface or closed surface equals the electric charge enclosed Q over epsilon 0. Okay, so it's a very, very beautiful physical theorem, and it's of course the foundation of the Maxwell equation. And however, as I have said, it is about a surface, so therefore it involves the electric field at the various point of the Gaussian surface. So it is sometimes, or I would have to say, it is most of the time very difficult to calculate this surface integral. Therefore, we would like to convert it into a differential form. Differential form consists of the divergence we have just defined. It is surprising that it could be converted into such a simple form. It says that the divergence of electric field is proportional to the charge density over epsilon 0. It is so simple. So first, we have to connect the divergence with the surface integral. So first, we will prove a very, very beautiful mathematical theorem. So this is a mathematical theorem we will apply to the case of electric field. However, it is not just for electric field. You have to remember, it's a mathematical theorem for any flux. The key observation is that we have already started a discussion last week. When we divide a volume into two parts, for example, this whole volume, we divide it into two parts. Here, I cut it in the middle into A and B. So it is a key observation that the electric flux through A plus B, the whole volume, equals to the sum of flux through A plus the flux through B. The reason is simple. If you add phi A and phi B, the contribution from the interior faces, we call it SAB here. You can see there's a SAB, that's the overlap of the A and B, the two regions. On the surface, the contribution from SAB will cancel out. What I mean is that looking from the part A, the volume will be like this. And for SAB is part of the surface with the direction pointing from inward to outside, so it would be N1. However, looking from region B or part B, SAB is also part of the surface. However, now it is the direction of the surface, again, pointing from inside, outside to outside. It is in opposite direction. Here we call N2. So here I say the outward normal direction of SAB from part B is opposite to direction from part A. Okay, here I indicate what I'm talking about. Therefore, but the electric field on the surface AB has only one direction. So if you multiply the electric field with N1, it will be opposite to you multiply the electric field with N2. N1 and N2 are opposite to each other. Therefore, when you calculate the electric flux, the contribution from N1 for the phi A will cancel out the contribution from N2 for phi B. Okay, therefore, it will cancel out. What is left is only on the outer surface. By outer surface, I mean here and here. Remember, here and here, putting up together is just the surface of the original region, right? Therefore, I can say for sure the electric flux from A plus B through this whole surface is equal to phi A through this surface plus phi B through this surface. Again, that's because in the contribution from the middle, the interface, the intersection cancel each other. Okay, so it is a tremendous observation. You have to remember it at every step of our derivation. With this in mind, I can divide any Gaussian surface into small cubes. For example, if I have this kind of Gaussian surface, the inner space of this Gaussian surface can be divided into small cube dV, as it is shown on this diagram. Okay, and the point is the sum of all the flux through the cubes equals to the flux through the original Gaussian surface. The reason is simple as the earlier page, because all these small cubes overlap. On the surface of overlapping, the contribution to electric flux will cancel because they are pointing to different direction for the left-hand side and right-hand side. So if you add the electric flux of the two cubes together, the contribution from the interface will cancel out. Therefore, you add up all the surfaces, you add up all the flux through all the cubes, of all the overlapping contribution cancel. So what is left is only on the outer surface. Okay, and don't forget the contribution to the outer surface is just the electric flux for the original Gaussian surface. Okay, therefore, again, this is a tremendous observation. That means you can calculate the flux through any Gaussian surface by calculating small cubes. So let's calculate the flux through a small cube and see what we can do from there. Here is a small cube. This small cube, for simplicity, I simply choose that it is put in the space in this way. One of the edge is along the x direction, the other along the y direction, and the third one along the z direction. So it will be easier to calculate. And eventually, we are going to send this small cube into infinite small. Therefore, the orientation or size really doesn't matter because we are taking the limit at the end. However, put in this way, the flux through this cube is much easier to calculate. I can calculate the flux through all the surfaces. For example, here I count the flux through the right-hand side and the left-hand side. By right-hand side and left-hand side, I mean the two surfaces perpendicular to the x-axis. So it is this one with the dA here, and this one, the left-hand side, with the dA here. Okay, so for the right-hand side surface square, and both of them are square. That's why it is easy to calculate. So for the right square, dA is pointing in the x direction. So when you multiply E with dA, it gives you EX times dA. EX evaluated at x plus delta x because the position of this point is x plus delta x. So this is the x component of electric field times the surface of the square would be delta y, delta z, because I assume that the length of the edge is delta z and delta y. It is not listed on the diagram, but it is obvious from observation. Okay, so this is, maybe I'll put it in next time. So this is delta y, the delta z, and this is delta y. Therefore, the area of the surface of the square is delta y, delta z. For the left-hand side, dA is pointing in the opposite x direction or negative x direction. Therefore, it is equal to minus Ex times delta y, delta z. But remember, this Ex will be the electric field on the left surface. Therefore, it is evaluated at coordinates x instead of x plus delta x. Therefore, there is a difference between the electric field, and therefore there's a difference between the two electric flux. However, this difference is easy to calculate because it is, if you look at the Ex as a function, a multivariable function, then this is just the difference of the function with respect to the difference of coordinates delta x. And this is while keeping y and z the same, constant. Okay, so the difference of a function while keeping y, z constant will be called Ex over partial Ex, partial x, the partial derivative, times delta x. Therefore, the difference between these two electric flux can be easily calculated as partial Ex, partial x, times x, the difference in function, times the area delta y, delta z. Okay, we finish the two surfaces on the left and the right. And we can do it again. For the surface on top and bottom, it is easy to show that it is equal to partial Ey, partial y. Again, Ey, because it is the surface is on the xz plane, and therefore dA is in the direction of y. Therefore, it pick out the electric field, the y component of electric field. And I'm calculating the top and bottom, so the y will change in the calculation from y to y plus delta y. Therefore, there will be a delta y here. Okay, and the surface area of the surface is delta x times delta z. So delta x, delta z. Okay, I hope it's clear to you and you think a little bit, not that difficult to identify the difference between the top and bottom. The difference of electric flux of the top and the bottom equals to partial Ey, partial y, times delta x, delta y, delta z. Therefore, we have two left, which is the front and back. And it's not difficult to see it is partial Ez, partial E, partial Z. Therefore, when we put everything together, the sum of the flux on the 6 square surface could be written as partial Ex, partial x, plus partial Ey, partial y. Here, the top and bottom, partial Ez, partial z, front and back, times delta x, delta y, delta z. The point is, it's the same factor. Delta x, delta y, delta z is just the volume of the cube. And the front in the square, the front formula inside the parenthesis is just the divergence of electric field. Okay, so it's hard to believe this calculation could be simplified into this so simple an expression. Again, that means the flux through a small cube is equal to the divergence of electric field times the volume of this small square. We assume that, of course, it's a cube. We can eventually, we are going to send the delta V goes to 0. That means the volume of the cube will be shrink to very, very, very small. Okay, so we assume that when it is shrink to very, very small size, it doesn't matter whether it's a cube or not. Okay, from looking from outside, you can only see a very volume over there. Whether it's a square, we think it does not affect the result. Okay, so we think that this result apply to any shape of small volume, not just small cube. Even though we from the beginning, even though here we derive it from a cube. Okay, so what we have is a definition or a physical meaning of the divergence of electric field. The divergence of the electric field, if you divide this delta V to the left-hand side, pull this delta V to the left-hand side, you get the divergence of E equal to the flux through this cube over delta V, the volume of the cube. So we usually say the divergence is the flux of the vector field per unit volume or per unit volume. Better remember this result because it will be used very soon to calculate any flux through a surface. Okay, so for a small cube, the flux is equal to divergence times its volume. And we have already told you in the earlier transparency that the flux through any Gaussian surface is equal to the sum of flux through all the cube comprising this Gaussian surface. So phi E for the whole Gaussian surface equal to the small phi E, phi IE. I means that we number the small cube by I. 1, 2, 3, 4, 5. Of course, it's a huge number. However, theoretically, we can do that. So for the small ith cube, the 第 I 个小的方块 the ith cube, the electric flux we designated as delta phi I, and we sum over all I. Of course, it's a huge number, but theoretically, we can do that. However, delta phi, we already know how to calculate it because it's a small cube. So its electric flux through the small cube equals to the divergence times its volume. So it is gradient dot EI, divergence, times delta VI. And sum over I. Then if I assume that we cut the small cube into small size and the number of the cube into send the number of the cube into infinity, then this sum over becomes an integral. Okay, integral over what? Integral over the volume of the integral of the volume inside the Gaussian surface. Okay, so this is the integral of the divergence over the volume inside the surface. It is called a volume integral. Okay, what we arrive at is a tremendous mathematical, again, it's mathematical theorem because it's not just about electric potential, electric field. No, I didn't assume that this, even I use the notation so that you feel familiar with it. However, this theorem, the whole derivation and the statement does not depend on whether this E is electric field or not. Okay, it could be any field, but with the name, we call it E. Okay, so this mathematical theorem is that the electric flux, the E flux or E surface integral of E equal to across through a Gaussian surface equals to the divergence of E over the volume inside the Gaussian surface. It is tremendous mathematically because, again, let me emphasize, it is true for any vector field. So on this page, I changed the notation from E that indicate it's an electric field to A, any vector field. Okay, so it's a formula, it's a theorem applied to any formula, any vector field. This is usually called divergence theorem, or sometimes just called mathematical Gauss's law or Gauss's law. It is originally invented by Gauss. Somebody will say it is the greatest, not just one of, but the greatest mathematician of all time. Anyway, it is so important because this integration is surprising. This integration on the right-hand side is an integration inside a volume, but it is related to the quantity on the surface. On the surface is outside the volume, so it's not connected. It is connected to the volume, but it is not inside. Outside and inside is not separable. Usually we'll think that the inside and outside are two separate area. However, this theorem tells you that if the quantity A has some good behavior, for example, it is continuous, it's differentiable, then the inside and outside is not totally unrelated. Okay, it is related in this way. Again, the integration in the inside is related and surface integral on the outside. Okay, so and think carefully, it is not so surprising actually, because we have met this kind of connection once in calculus. In calculus, the fundamental theorem look like this. The derivative taking an integration is actually equal to fb minus fa. FA is the value of the function at the two endpoints. The left-hand side, the integration is the inside between the two endpoints. Okay, so somehow these Gaussian law or divergence theorem is a little bit related to the fundamental theorem of calculus. Okay, or you can see a little bit connection here. So it is surprising, but it is not surprising at the same time. Okay, so now up to this point, everything is mathematical. Finally, physics. Here, again, our goal is to convert the physical Gauss's law from integration formula to the differential formulation. Okay, so now what I'm going to do here is to derive the differentiation formulation first. It is easy. I can just apply the integral formulation of Gauss's law to a small cube. Well, the integral formulation of Gauss's law is applicable to any Gaussian surface. Okay, so it is also applicable to a small cube. So if I apply to a small cube, then the electric field EdA, the surface integral, or I could say electric flux, equals to the divergence dot delta V, according to the mathematical Gaussian law. And according to the physical Gaussian law, this electric flux must be equal to Q over epsilon 0. So this step from here to here is physical, not mathematical. Okay, the physical Gauss's law tells us the flux equals to the charge inside the Gaussian surface. Okay, so if I denote the charge inside as Q, and this Q could be calculated from the charge density. If this cube is really very small, then the charge density inside it is uniform. Uniform means this rho is a constant. Okay, so this Q could be written as rho times delta V over epsilon 0. And if you connect the term here and the term here, you can easily observe it shows you that the delta E, the divergence of E, is equal to rho. Okay, it's simple. Okay, so if I put it in language, I would say we have already proven that the divergence is the electric flux per unit volume. And by physical Gaussian law, electric flux is also equal to the charge, is also equal to Q is also equal, rho is also equal to the electric flux per unit volume if you take this delta V to the left-hand side. So rho is also proportional to the electric flux per unit volume. Therefore, it connects the divergence of E and the rho. Okay, ladies and gentlemen, that's the differential form of physical Gaussian law. Div E equal to rho over epsilon 0. Okay, so this is the differential formulation of Gauss's law. I have to emphasize this is an equation true for every point in the space, because in this equation, there is a divergence E at every point in the space. So if I want to write it explicitly, the left-hand side is actually a function of R. On the right-hand side, rho is the charge density, and also we could define a charge density for every point in space. Sometimes it's uniform, then rho is a constant, but sometimes the charge distribution is not uniform. It could vary in different places in the space, and therefore rho could be a function of R also. Therefore, this equation, the left-hand side and right-hand side are both functions of R. That means this equation is true for every position R, or in other words, for every point in the space, this is true, okay? So from a formulation of Gauss's law that needs a Gaussian surface and in a global view, then we go into indifferential formulation of Gauss's law, which only depends on things that happens locally. Okay, on the left-hand side is a physical quantity defined on R. On the right-hand side, it is also a physical quantity that depends on R. So what happens at R is determined by what happened at R. So it's almost like a 在地化. Okay, it's like a localization theorem. Okay, localism. 在哪里发生的事情，就由当地的人来决定。Wow, I mean, I'm not talking about politics, but sometimes this formula indicate this kind of thing. Okay, so intrinsically, this equation tells you the electric line accumulation of a unit volume is proportional to the charge density. That's the essence of the differential formulation of Gauss's law. Okay, so on this page, I derive the differential formulation from integral formulation. Next page, I'm going to do it in reverse. I take this differential formulation as a fact. Now, I apply it and plug it into the divergence theorem. Divergence theorem is the mathematical theorem. It applies to any vector field. And of course, it is applicable to the electric field E. The divergence theorem, again, please recall, it tells you the surface integral of E equals to the volume integral of divergence E. So if you plug in this differential form of Gauss's law into the right-hand side, then the right-hand side becomes the integral over volume, or volume integral of rho charge density over epsilon 0. On the left-hand side is still the electric flux, or the surface integral of E. On the right-hand side, the volume integration of rho is equal to Q. That's the definition of charge density, isn't it? Okay, so the right-hand side equals to Q over epsilon 0. So connect the first term and the third term, it becomes the surface integral, that is the electric flux equals to Q over epsilon 0. That's the integral formulation of Gauss's law. Therefore, in the first page, I derive the differential formulation from integral formulation. On the second page, I derive the integral formulation from the differential formulation. Therefore, it proves the integral formulation and the differential formulation are equivalent for Gauss's law. Okay, so I think it's a very, very important result. Okay, you can use either the left or the right, integral or differential. Okay, and it also tells you the Gauss's law of the magnetic field, that the magnetic field does not have any magnetic charge into the divergence of B is always equal to 0. Okay, that's the second. So we convert two of the Maxwell equation, those related to the surface integral, into a differential form using the divergence. Okay, that's the essence of our calculation here. Okay, so B is on here. Okay, as an example, before we take a break, as an example, I can calculate the I can calculate the divergence of an electric field inside a uniform charge sphere. Okay, remember I think in Gaussian in general physics, Professor Liu has derived an electric field inside a charge uniformly charged sphere like this. If you recall, the result is that for uniform charge density with charge density rho, the electric field outside, of course, it is E proportional to minus R squared, minus 2 squared. Okay, 1 over R squared, sorry. And however, inside the sphere, using the Gaussian integral Gaussian law, it could be derived that the electric field is proportional to R. That means it decreases as it approaches the center of the sphere. So now I can calculate delta E, the electric flux. So now I can calculate div E, the divergence of the electric field, by plugging this formula. Okay, therefore, the electric flux inside the ball is equal to rho over 3 epsilon 0. That's the constant in front, and the divergence of R. So essentially, this is a calculation about the divergence of R, the vector. However, it is easy to see that the divergence R is equal to x of partial x over partial x plus partial y over partial y plus partial z over partial z. Partial x over partial x equals to 1. So is partial y, and partial z. So the sum of the 3 factors in the parenthesis is equal to 3. And 3 cancels the 3 in the denominator. The right-hand side is equal to rho over epsilon 0, as we would have expected from the differentiation. Okay, so by calculating electric flux, if you know the electric field in advance, then you can calculate the divergence, then it will give you the charge density at that point. That's the essence of the differential form of Gauss's law. Again, if you calculate the divergence, it will be related and proportional to the charge density at that point. Okay, let's maybe take a break. And therefore, okay, so in our exercise, we also did the other, in our homework, we also did another exercise to calculate the divergence of the electric field outside a point charge particle, okay, which is 1 over R squared. Okay, you can do this, and we'll talk a little bit about it in the later lecture. Okay, so let's take a break. Now, I'm going to move on to the next topic, which is the Ampere's law. With here, we will relate the line integration to the curl of a vector field. Okay, let's take a break here.